Okay. This week, I don't know. Last week the recording went without sound. This time it may go with sound only and without image, as I see. But through a couple of iterations, we'll get back to production line as we did in the previous semester. Very good. So we are continuing. So here is overview of the class with 4 chapters, and we meeting number 4, recursion relations. Here is the guy whom you should blame if you do not like today's meeting. And here is our plan. So it's all recorded, but if you just follow what is on the slides, I think it will be boring and not comprehensive. So how did we set up our main equation last time? We want to express the quantum state composed of 2 lower level small systems as summation of the basis states of system 1 and system 2. This set of coefficients J, J1, J2, 1 and 2. What if we follow, some people use different order of the indices, and what if we multiply this expression by the bra vector from the left? Bra from left. We keep the same total momentum, J1 and J2, because we know that in this expansion, the J1 and J2 values are set up. We are not changing them. If we are getting triplet as a summation of 2 spins 1/2, we get different projections of magnetic momentum, but we do not change the actual spins. We do not cheat and replace spin 1/2 with spin 3/2 as we go. So J values stay constant. We do not tweak it. But the second pair of indices can be different. M1 prime, M2 prime. Gm summation M1 and 2. C with all this enchilada. And here we have J1, J2, M1 prime, M2 prime, J1, J2, M1, M2. So even if you're not comfortable with Bryant-Cat notations, which we should be, it is shorthand notation for wave functions, and product of Bryant-Cat corresponds to either integration if they are in continuous space, or scalar product if they are in discrete space. But we need to know only two simple things. If the indices coincide, it will be 1. If indices do not coincide, it will be 0. M1 is not equal to M1. Right? So it is orthogonality relations. So this bra and cat notations for good functions include in themselves orthogonality relations that we do not want to waste time in details. And here we do have two indices to compare: M1, M1 prime, and M2, M2 prime. So this underlined expression is converting into two delta functions. One M1 prime M1, second M2 prime M2. So what was the program going to click? What was the reason to multiply the expression by the bra vector from the left? Does it sound?
To get eigenvalues.
To get rid of wave functions. We hate wave functions because they're big. We want to play with numbers. No operators, no wave functions, only algebra of numbers. So when we multiply bra times cat, or wave function star, wave function integration, we get rid of wave functions, we get a number. So here our number is delta, product of delta functions. This is also a number. So it is a convolution of this product of two basis functions. You can and the quantum rotational state of a bigger system, which may or may not coincide, which may or may not give some numbers, or maybe it will be something other than zeros and ones. So after we plug in these delta functions and perform the summation, what happens?
M1.
So if you were here for quantum 1, you are tired of these old jokes. But if you're here for the first time, you may enjoy it. So summation is like a snake that chases a rabbit, and they eat each other and disappear. So if you see summation and delta function, you get rid of it. Right? So it's a math. And as a price for this trick, one needs to unify two indices. So the index, this one and this one, should become the same. So if the delta functions look the same, we should replace each M1 to M1 prime. And then we do not have sum, and we do not have delta functions. Also for, instead of M2, we will write M2 prime. So the left part doesn't change. J1, J2, M1 prime, M2 prime, J capital, M capital, equals, now we do not have summation, but we still have the coefficient. J, M capital, J1, J2, and we replace M1 to M1 prime, and M2 to M2 prime. And we do not have delta functions, because they disappeared because of the math. So it's kind of silly derivation. One can postulate it right from the first line, but it is a new notation, another notation for Clebsch-Gordon coefficient. So it is convolution of the quantum state of the bigger system with product of quantum rotational states of lower rank systems. This one can always be replaced to G1. G2. So we took maybe too long time for this simple introduction, but a lot of textbooks do not use this C coefficient with C index. They follow the Bryant-Cat notations. Any objections, arguing, blaming the author of this theory? It's not me, I'm not responsible, I'm just communicating. So we are combining angular momentum of two lower rank systems into big momentum of combined system. Like if there are two electrons, or electrons that has spin degree of freedom and orbital degree of freedom. And we are getting some special laws for this addition. Okay. Administratively, we got handouts with Rankach variable. And we got the handout from Quantanucci textbooks. So we are done with defining angular momentum addition in Bryant-Cat notation. Now we are writing down this expression and we are replacing the C symbol with this bracket stuff, and then we are going to apply raising operator to both left and right sides. Good? What are we going to get in the result? We are going to get several C coefficients.
Thank you.
I should try different one. Gesundheit.
That works.
Different coefficients with different distribution of the magnetic quantum numbers are related to each other. So the main idea of what we are doing is that if we are on the inhabited island, if you do not have this table and we do not have internet, how can we get values of these coefficients? So the idea that we find one and then we expand to another ones through recursion relation. Today, well, we are not going to do everything, but we will show how these recursion relations are coming up. So we just preparing backup in case we will be on the isolated part of the universe. I wish we never use the skill, but who knows?
It'll be good for Comcast users. Get it?
No, he doesn't.
We should trim this part of recording and set it to Comcast.
Oh no!
Do you have Soundcast?
No,
Do you have the-
not anymore. Yeah, no, I have cable one.
I can tell some good things about Comcast.
Yeah.
When we were staying in Los Alamos at like isolated guest house that didn't have internet, and we requested connection from Comcast, it came 1 month later. But just to satisfy one customer, they brought excavators. They did a trench, put a cable, just by a request.
Wow.
And they didn't charge for this. They charged just monthly fee.
Wow. That's not bad. That's not money.
So if you look on the on the small screen, which probably you don't see. You need bigger screens. Actually, I've got feedback from the class in the last semester, and I was fearing that there would be critical feedback about the content. No, the main criticism was screens are too small. It is your fault as a teacher. And the suggestion was insist that everyone sits on the first row. I don't know if you got it, but it is the ideas and feedback from colleagues. So J1 plus minus greater detecting J1 and 1 is providing yes plus minus J1 and 1 plus minus 1. Right? It is what we practiced last time. And if I do not want to think, but I like calligraphy, I can repeat this equation 3 times. All work, no fun. Just replacing the indices. J2 plus minus J2, A2, H is plus minus J2, A2. There is no reason to do this. You can just imagine how it looks like. G capital plus minus G capital and capital H bar is plus minus J capital M capital J capital and this S plus minus function is a mask that either stay as a factor in front of the result, or it becomes 0 and disables the result, as we saw on the same board last time. J plus 1 minus M plus minus 1. So plus or minus is very important. So if we are dealing with raising operator, it is plus. If you're dealing with lowering operator, it is minus. And you see that for some examples, like if M equals J, this factor becomes 0. That forbids us to jump higher than ceiling or fall lower than floor. Right? Okay. Nothing smarter on this slide. Okay, a little better.
I have a question.
Please.
Why, for the total system, does M not change?
Because I was in rush and I didn't wrote it appropriately. Thank you for catching it. It's so non-creative to repeat the same.
I didn't know if it was special with.
No, they are the same. And since everything what we are doing is based on the fact or assumption that these spins do not interact. So the M and J for system 1 and for system 2 are good quantum numbers. And since they're not interacting, their operators are additive, or many sort of operators, like including the creation and annihilation. J1 plus minus plus J2 plus minus. With understanding that it is multiplied by unity operator in respect to system 2, and here it is unity operator in respect to system 1. So when we, nothing new, this was what we discussed last time. Now we are going to apply this operator to this expression. Okay? With plus sign. G plus applying to J over M. Summation and 1 and 2. So we could place it in front of sum, but since quantum operator doesn't affect summation sum, we can put it inside. And I will write something quickly and then erase it. You may just wait to save space on your notes. So I can put J plus this hat here. But since we are going to act on the so there will be coefficient, and then there will be ket vectors corresponding to lower rank systems. J1, J1, J2, and 2. Since we need to act on them, having this big operator doesn't have any sense. We need to plug in its implementation in this form. So we will just write here J1 plus J2 plus. Here I need to practice calligraphy. J1, J2, and 1 and 2, J capital. Okay? So, in all of our meeting, there is only one creative step. The rest is boring algebra. And the creative step is not very great. It means that if we apply operators that act either on one or other system, we can, instead of having summation and then one term, we can treat it as two different summations. One summation will contain J1 operator plus operator, and another summation will contain J2 plus operator. Make sense? So we'll repeat the same line twice, but in one case we keep only one raising operator, in second line we keep the second. Summation M1 and 2 J1 plus this stuff. Plus summation M1 and 2 J plus again this coefficients J1 and 1 J2 and 2. Okay, from now on we will just plug in whatever is written there and get the answer. It is a little technical delay, and this board may not be sufficient. After I'm done with it, I will erase the first board and keep writing there, but the answer is straightforward, very close. So, and to save our time, I will not open this definition of the prefactor until very last minute, because this s plus minus is much shorter than the square root. G plus here, we are getting s plus, which is not an operator anymore. It is a factor. And here we have J, 1 plus 1. Here we have G, the summation, 2, applying the J1 plus operator. We do not touch the Gordon coefficient. So the operator actually acts on Brian cat. And here, this operator affects only on the wave function of the first system, right? So the only difference is that we get S plus of J1 and 1. And here we're replacing G1 the same and M1 plus 1. Right? This factor is replaced by this factor. And this factor stays the same. G2 and 2. So we are applying raising operator only to the first angular momentum system. Second term, again summation in 1 and 2. Coefficient, Clebsch-Gordon coefficient is not affected by the operator. And now this J2 operator affects the second system, second factor. So S plus of G2 and 2, G1 and 1 unchanged, G2 and 2 plus 1 get change in the indices. And here I'm practicing calligraphy and J1, J2, and 2, J2. So, what is our goal? Tactical goal, not general career goal in that. Here, for next few minutes, we need to get Clebsch-Gordon coefficients with different values of M1 and M2 and find relations between them. Like maybe if we swap indices, it will be minus sign in front, or maybe some factor, right? Is it a question?
Yeah.
Please.
S plus is a function of Jm is acting on Jm plus 1?
No. The indices come from the original statement, from the original wave function on which we act.
Okay. But this is acting on Jm plus 1.
No, it's a number.
Look, let's look here. Operator J plus acts on the state
Oh,
Jm. As a result, we browse in the space of indices by incrementing m to plus 1, and we are getting the factor, which is not an operator anymore. It's just a factor in front of this wave function. So this is wave function, and this is number.
oh, okay.
This is wave function, and this is operator. Okay? Many thanks for asking this. Otherwise, it could be too much mess. So we need to simplify this long summation in such form that we will keep only expressions like this with different indices, and then they will be equal to each other or equal to each other with some factors. But we do not have any intention to keep wave functions. Right. Can you verbalize it once again loudly with complete sentence?
We take the wave function and we conjugate it, so then we use delta functions to kill the sums and we get numbers.
Exactly. Make sense? So we will use the same trick as we did in definition to get rid of wave functions. So we are doing something to remove this one, and this one, and keep only the numbers. Okay. So I'm going to erase everything in here and continue. this board will be sufficient to finish. It will be not long. And hey, we have completed 2/3 of our plan. We applied ladder operator to main equation. So we just looking forward to get the recursion. So multiply from the left by bra vector. J2, M1 prime, M2 prime. Onto the first one, J, M plus 1, and we will keep this S plus J capital M. So it is on the left, and now on the right, we keep summation M1 and 2. We keep the Gordon coefficients for J1, J2, M1, M2, and J. And then we are using this artificial bra on the right side as well. So here will be artificial bra.
Does it matter that you changed M and J?
No. It is not a good style of me, but nothing is wrong. I'm under influence of several sources, and they using different conventions. So here will be J1, J2, M1, M2 with primes. And here we have J1, M1 plus 1, J2, M2, right? Well, I still need to complete second line and fill the board, but you may get an impression where the recursion relation will come up. Originally, we applied raising operator, and here we increased the magnetic quantum number by 1. But now, by doing convolution, we will be setting up an equality with, on one hand, on one side, there will be, oh, this is one, it should be this one.
Okay.
One value of magnetic number, and here will be another value of magnetic number. But through some math, we will establish equality between them. So recursion is object of the same nature, but with different indices are set up in some relations. M1, M2, repeating unchanged J1, J2, M1, M2, J vector, M capital. And here I am missing S plus of J1, M. Here I need S plus of J2, M2. And now I'm placing this artificial bra. J1, J2, M1 prime, M2 prime. Convoluted with J1, M1 and J2, M2 plus 1. Whew. And here is the plus sign. We are almost done. We should be done in 2 lines. Unfortunately, the lines are long, but just 2 long lines. So by now we do not have wave functions. We will have convolutions of bra and cat. And we know that bra and cat always turn into number. And if the functions are orthogonal, these numbers are delta functions. So our very little tactical goal is to convert these convolutions into delta functions. Delta for first term and for second term. So for the first one, it will be index M1 should be equal to index M1 prime should be equal to M1 plus 1, correct? So the magnetic projection in system 1 should be equal, and it uses different indices in original and secondary notation. So M1 prime equals M1 plus 1, which means delta M1 prime comma M1 plus 1. And for the second system magnetic projection, it will be trivial. M prime equals M2 prime equals M2, which means delta M2 prime M2. Okay? For the second system, it will be opposite. M1 prime equals M1, trivial situation, delta M1 comma M1 plus 1. And for the magnetic projection of the second system, M2 prime equals M2 plus 1. M1, M2 prime, comma, M2 plus 1. So we are going to observe the snake and the rabbit once again. What will be the price if we remove? I'm just suggesting that we do not rewrite this expression by replacing this stuff with delta functions. If you want, I can, but there is not much reason. This one will be okay. I can write them here in the under bracket. Delta M1 prime M1 times delta M2 prime M2 plus 1. And here will be delta M1 prime M1 plus 1 times delta M2 prime M2. So we do want to get rid of these delta functions and these summations. And as a price for it, we need to, so we are getting rid of M indices without prime, M1 and M2. So everywhere where we observe M1, we need to replace it by M1 prime, but with respect to this delta function. So this means that we replace M1 to M1 prime minus 1. You see? I suffered of missing this logic for many years. If you are catching it immediately, very good. So it was plus in the original, in delta function, but after summation, we are getting minus. For the first term, and for the second term, we are replace M2 into M2 prime minus 1. Good. So first M 1 equals, so we still have first and second term, but no summation anymore. Now I'm writing this Clebsch-Gordon coefficient J1, J2. Instead of M1 in the first term, I'm writing M1 prime minus 1. Instead of M2, I'm writing M2 prime. Vertical line, J capital N capital. Times S plus of J1 M1 prime minus 1. We are done with the first term. So the wave functions and delta functions are removed. Now the second term. Yes. G2. So here we are replacing M1 to M1 prime without change. But the second index we are replacing to M2 prime minus 1. Times S plus J2, comma, M2 prime minus 1. In principle, we are done. I would like to maybe wrap it up in a more comprehensive style, but by now we already achieved the goal. Maybe it's not yet practically useful, which is very easy to polish, but we do see Clebsch-Gordon coefficients. You see 6 index object here, there, and there. Clebsch-Gordon coefficients with different distribution of magnetic numbers, m capital plus 1, m lowercase 1 minus 1, m lowercase 2 minus 1, and some factors in front of them, which are numbers. Meaning we can set up linear combinations and express one Clebsch-Gordon coefficient out of another one. So we need just find just one, and then we roll up system, same as one solves linear algebraic equations. So what can we do? I suggest, this is general, this is full recursion relation. But let's focus on the simple one, just a more particular case. For example, if we are looking onto the values of m capital equals j capital. So we are not looking on everything in general, but for example, if we are making singlet state out of 2 spins, 1/2, right? M equals 1, or J equals 0, totals we are looking for singlet, and then magnetic number is also 0. So how does this full complete recursion convert if you plug in this value? So here are delta functions that we just discussed on the board, and it is an expression that we do have on the board right now. So now we are going to look what will happen if m equals j. Do any of you have urgent appointments to go? Okay. I plan to finish in like 5 minutes. It shouldn't take much of your time. Well, your time is a precious resource. It shouldn't be wasted for boring formats. So we are approaching the practical side of this recursion relation related to your homework. So if we set up m equals j and we are rewriting this expression, so the s plus of j and m equals j will be equals square root m plus 1 minus m plus 1 equals what? 0. Meaning if we are exploring the magnetic projection bigger than total spin, it is not allowed. This is nature. Therefore, first left part is 0. Then on the right side, we do have G1, G2, yes, prime, G capital, J of capital prime, capital equals J capital times S plus J1 and prime minus 1. Plus G1, G2, M1 prime, M2 prime minus 1, J comma M equals J times S plus J2 M2 prime minus 1. So here we are looking only on a smaller subset of Cleford coefficients, but this will help you to complete the homework. So if we set up the J1 equals 1/2, J2 equals 1/2, M1 prime equals 1/2, M2 prime equals 1/2, J capital equals 0, and M capital equals J equals 0, it will help you to help us to find out the Clebsch-Gorlin coefficients for composing single state out of spin 1/2 states. We are doing a silly activity because you know from childhood how to compose singlet out of two spins 1/2, right? They just antisymmetric combination. Up, down, minus down, up, with 1 over square root of 2 in front. But now we are using armored tank to kill the fly. We'll show with efficiency how this high-level theory can solve simple problems. So these long and boring expressions are unknowns. And this is something that we need to plug in. And we will do it. Should I leave this exercise more for your homework or probably approach closer to answer to save your time? Any like decisions? I'm excited to write a couple of lines more and thank you. So the answer J equals 0, M equals 0. We know that it will be Gordon coefficients times this 1/2 minus 1/2 and here 1/2 minus 1/2 plus 1/2. I hate these notations. I do not blame you if you hate them too. This means that J1, J2, 1, and 2, J1, J2, and 2. So it is summation of the first spin up, second spin down, and first spin down, second spin up, with unknown coefficients. And these unknown coefficients have this long and boring sets of indices, which are written here. So we need to find what to plug into this empty spots. Now I'm returning back to our recursion, and I'm plugging the distribution of indices there. 0 equals so J1 equals 1/2 and M1 prime minus 1 will be 1/2 minus 1. Let's keep the same as here. 1/2 minus 1/2. 0, 0. So now we need to plug in S plus, plugging in here 1/2 minus 1. So S plus of the 1/2 and minus 1/2, which will be square root. Here the hardest part. I wanted you to do it at home, but I'm just excited. And it is not really so hard. So 1/2 times 1 plus 1/2, right? Because J and J plus 1, right? Minus minus 1/2 times minus 1/2 plus 1. So here we need 1/2 times 3/2, right? And here will be minus 1/2 plus 1/2 times plus 1. Good. And then minus times minus gives plus. So it will be 3/2 plus 1/2, giving square root of 4 over 2. So all this stuff in the first term converts into square root of 2.
It's 3/4
1 over
plus,
square root of 2.
no, isn't it 3/4 plus 1/4? Because 1/2 times 1/2 is 1/4.
Yeah, that first one wasn't distributed. Yes.
Okay.
Yes. Good. 1. Even better. Thank you.
I was like, oh, I need to go back to middle school.
I need that to middle school. Probably it would be a better idea to let you do it work. Okay. So we are continuing to expanding this expression, the real person expression. Plugging in the distribution of coefficients in here, which will be 1/2, minus 1/2, 0, 0, and then the hardest part of the square root. So it will be s plus of 1/2, comma, and here will be the same, 1/2 and minus 1/2. So it will be just 1 times. What do we get out of it? If, just for simplicity, we can probably call this A and B. Otherwise, we are good tired to write in the physics because we're just and we do see that 0 equals A times 1 plus B times 1. Which means that A equals minus B. Right? So the great result is that they are they have opposite sign. What is missing? Normalization. Summation of squares of these two coefficients should end up into 1. A absolute value square plus minus A absolute value square is 1. A square equals 1. A equals what? 1 over square root of 2. Right? So I shouldn't give more details on normalization. And then we replace A with 1 over square root of 2 and minus A with minus square root of 2. And the main result is that singlet 0, 0 equals 1 square root of 2 spin 1/2 up, spin 1/2 down, minus 1 square root of 2 spin 1/2 down, spin 1/2 up. I'm done. It's your time to ask questions if you do not feel comfortable with this. Anything sounds not very logical or unclear? Better ask now. for problems like this, one doesn't need this high caliber theories. One can get it much easier. But if you get higher values of momenta, this is probably the quickest way to get something with them. So we didn't use initial value. We didn't use analytical expression for value of A. We got it out of normalization. But there are additional equations that allow to find one value analytically and then expand for the second one as we did here. What is your homework then? Just maybe summarize it in such a way that it will be readable. So you are masters of Clebsch-Gordon theory of angular momentum addition from now on. When we meet next week, we'll try to establish bridge with practical applications. So I will try to review the notations for high angular momentum in heavy metal iron and make connection to what we did before. What is missing? Meeting number 4 is over. Thank you for coming, and I'm going off record.
So Tuesday.